All right. So let's go ahead. And get started with this. One of the things that we should be able to do based off of yesterday, if I give you a chemical formula such as, well, why isn't it showing up? Oh, because it's in one. All right. So if I give you a chemical formula such as potassium permanganate, all right, KMNO4. All right. So right now, what are some things that we should be able to determine about this chemical formula? All right. So yesterday we learned how to determine molar mass or formula mass, and really it's the same thing. As far as our purposes in this class, I'll use the term interchangeably, either formula mass or molar mass. So in order to determine the formula mass, what do I need to know? I need to know the mass of each element, right? So I need to know the mass of potassium, I need to know the mass of manganese, and I need to know the mass of oxygen. All right? So I only have one potassium, so for potassium I have, what's the mass of that? 39.10, I guess. Yeah, 39.10. All right. Manganese. What is the mass of manganese? 54.938, so 54.94. And what is the mass of oxygen? 16. But what's special about the oxygen? Okay, we have 4 of them, so we need to account for 4 oxygens. So, real quick, what is, somebody calculate or tell me, okay, so oxygen is going to be 64. Now, what is the total mass, or what is the molar mass of potassium permanganate? All right. Bless you. So, does anybody not understand how we got the number 128? 128.04. 158? All right, sorry. That's all right. So, does anybody not understand how we got 158.04? All right, so all we had to do was add 39.10 plus 54.94 plus 64, and that gives us our total formula mass or molar mass. All right, now, the second thing that we learned yesterday was how to get percent composition. So if I wanted to know the percent composition or the percent of manganese in this equation, how would I determine the percentage of manganese in this formula? All right, so I'm going to take the mass of manganese, which is 54.94, over the total mass, 158.04, times 100, right? So that's going to give me what? Say again? 44.34. Thank you. .76% manganese. All right, so what would be the percentage of oxygen? So we take 64 over 158, 40 point what? 40.50%. All right, now, if I wanted to know the percent potassium, do I have to do it through the division? I add them together and subtract from 100. or whatever's left over from 100. I could do it that way, or I could just solve for it. So what is the percent potassium? .74, so about 26, 25 point something. 24.74. All right. So are we clear how to get this information now? All right. So formula mass, molar mass, what that tells us is this tells us the mass. So let me write this number over here. So in 1 mole, of KMnO4, our potassium permangate, is equal to, or is going to equal 158.04 grams. So if I want to measure out 1 mole of potassium permangate, I got to go to the scale and I got to measure out 158.04 grams. All right, let me let's do one more. So what if I wanted to know what is the molar mass of, and we did this one yesterday, but I want to just revisit this one. What is the molar mass of water? So we need to find out hydrogen and oxygen, right? Hydrogen is 1.01. We have 2 of those. So 2.02. Oxygen is 16. And remember, I want you to go to 2 decimal places for the atomic mass, so always round to that. So 2.02 plus 16 gives us 18.02. Now, that's fine and dandy. That tells me that water is 18.02 grams per mole. If I wanted to know, now we're going to move to this next step of it. If I wanted to know how many grams were in 2.5 moles, if I have 2.5 moles of H2O, how many grams is that? All right, what do I multiply by 2.5? Why? That's a gram per mole. So if I have 2.5 moles H2O, and I want to know grams, what I'm saying is that I have 18.02 grams per 1 mole, right? So this should be a little, right around 40, 38, something like that. 45.04. 5. Yes. All right. So let's move forward a little bit. Now, so one more thing I want to do. All right. If we're given another circumstance, we're still dealing with water, H2O, which is 18.02 grams per mole. And let's just say that I am telling you that I have 162 grams of water. How many moles? All right, so if I have 162 grams of water, how many moles do I have? How do I determine this? All right, so I have 162 grams H2O, and I want to know mole, and so it's 18 grams per mole, 18.02 grams. So that's going to cancel out grams, and so 162 divided by 18.2 gives us, say louder, 8.99 what? No, moles. I was looking for units. All right. All right. So 8.99 moles H2O. All right. That is going to, doing that calculation is going to be the big calculation that we're going to be doing today. That's going to be the main thing. So what I want us to do first is we are going to do a little bit of practice going from grams to moles, moles to grams, those type of things. But remember, you're going to have to calculate formula mass in that. So I don't really want you to take anything down from these pictures, guys. Don't really want you to draw these pictures or anything like that. But what I want to show you is the difference between an empirical formula and a molecular formula. The thing that you need to know about an empirical formula is a formula that is reduced to its lowest form. So basically, empirical formulas, we cannot reduce this any lower. We're saying we have 1 nitrogen, 2 hydrogens, and 1 oxygen. There's no reduction that can be done there. Whereas the actual formula is NH4 ammonium nitrate. So it's NH4NO2, which means basically we have 2 nitrogens, 4 hydrogens, and 2 oxygens. Do you see how this formula is the reduced form of this formula? If we divide everything by 2, we're going to come up with that number. All right, we have 2 nitrogens, so it's technically N2H4O2. If we wrote it standard, and then if we divided everything by 2, then we end up with that one. So empirical is the simplest form. Molecular is what's actually there in one molecule. So sometimes the empirical formula is the smallest form, or is the molecular formula. But most of the time, a molecular formula is the real formula, and empirical formula is just the simplest form of it. We can always solve for empirical, and then we have to determine molecular from the empirical. So it's a multi-step process. So today we're going to be mainly focusing on getting empirical. All right. Like I said, I don't really want you to copy the pictures or anything like that, because there's not really anything to get off of that one. So let's talk about empirical formula first. All right, so from this sheet, I really want you to have the definition of the empirical. All right, so an empirical formula consists of symbols for the elements combined in a compound with subscripts showing the smallest whole number ratio. So it is a chemical formula that shows the smallest whole number ratio of the different atoms in the compound. For our cases, if you remember in ionic compounds, one of the rules for creating an ionic compound is we always reduce. So for the most part, ionic compounds are always empirical. I know in my notes there it says that it's usually a compound's empirical formula. For the way that I showed you how to do ionic compounds, or naming ionic compounds, creating ionic formulas, we always reduce. So we're always going to have the empirical formula for the ionic compound. All right. For a molecular compound, and I'll say this a little bit differently, for a covalent compound, the empirical formula does not necessarily indicate the actual number of atoms present in each molecule. For the example that we have, the formula for the gas diborane is BH3. BH3 is the empirical. And the molecular formula is B2H6. Do you see the connection between the two? What was done to B2H6 to get BH3? We divided all the subscripts across by 2. All right. So, or another way to look at it, to get from the empirical to molecular, we had to multiply all the subscripts by 2. All right. So, today we'll determine. All right, so there's 2 different ways that we determine empirical formulas. The easiest way is if we're given percents of each of the elements involved. When we're given percentages, remember, if we're given percent of each element, what should the total of all the percentages add up to? 100%. So if we have 100% of something, we can assume an easy way to manipulate those percentages then is to assume 100 grams of sample. Because then the percentages that we have for each element becomes what? So if I have 78.1%, it's 78.1 grams of boron. And 21.9% hydrogen tells us that we have 21.9 grams of hydrogen. So that's going to be the easiest way to get this, is we just automatically assume that those percentages are out of 100 grams, and then we can determine the mass of each element present. Now, once we have the mass of each element, what can then we determine about each element? If we know the mass, we can determine what? Moles. All right, so if I wanted to find out how many moles of boron I have, what would I do? 78.1 grams of boron. How many grams per mole is boron? Or where would I find that out? 10.81. So I would say 1 mole of boron is equivalent to 10.81 grams. So I divide 78.1 divided by 10.81. That's going to give me somewhere around 7-point-something grams, 7-point-something moles, right? All right, so we have 7.2 mole. All right. Yes. Yes. All right. So I'm going to move to the next slide. We're going to continue solving this one and just kind of showing you steps. All right. So what we started talking about there, we already determined that we had 78.1 grams of bromine. We determined that we have 21.9 grams of hydrogen. Our next step in determining empirical formulas is to determine the moles of each. So to determine the moles of boron, like we said, we're going to divide it by 10.81 because that's the atomic mass of boron, and that gives us 7.22 moles of boron. For hydrogen, we're going to divide it by the atomic mass of hydrogen, which tells us that we have about 21.7 moles of hydrogen. So now we need to see these numbers in comparison to each other. So these give us a mole ratio of 7.22 boron to 21.7 hydrogen, right? Now, I can't write a formula that's B7.22 to 21.7. I have to get this to a small whole number, right? How can I get these two whole numbers? Well, if I divide 7.2, if I divide them both by the smallest molar value, that's going to mean that boron is going to be 1, and 21.7 divided by 7.22, it should be pretty close to 3, right? So I have a 1 to 3 ratio. So what that tells me is, what is my empirical formula for this? BH3. All right, that's pretty much it. All right, so we'll move forward. So let me see if I have another. So everything's going to be divided by 0.71. So that means that we have 1 here, 0.71. This would be 2, and 2.8 divided by 0.71, about 4. All right, so we have a 2 to 1 to 4. So that means that our formula, when I'm writing sodium, what subscript am I going to put by sodium? 2, sulfur, S, and then oxygen, 4. All right. Does this look familiar from something that you would have saw? Sodium sulfate. So if you look on the back, just to verify this, sulfate has what charge? -2. Sodium has a +1. So for an ionic compound, this works if we did crisscross. But you wouldn't have known that to begin with until you did that work. So the question was, is there any specific order that we write the formula in? If a metal is present, always write the metal first. From when we start with dealing with covalent compounds, general rule, hydrogen, then carbon. Our carbon and hydrogen are kind of subordinates. I tend to write carbon first all the time. Oxygen would be like the next most important. But really and truthfully, no, there's no order in empirical. Molecular, there's going to be a order, but that's because we start following the structure. We look for the central atom, the most electronegative. All right, so do we need to do another practice with this, or do y'all want to try some individual practice and come back? Individual. All right, so we'll pause right here.